Hey, what's up YouTube? Welcome to another video. Today we're going to be seeing number of islands. So as the problem says, given m and given a matrix of m times n, return the number of ones that are joined together. So that would be the number of islands. For example, in this case, in example 1, we have here a bunch of ones. We have like this grouping right here, which is connected by like this area and this. So the number of islands is here. Now, it's very important to see also that you may assume that all four, okay, so this in that outside there's only water, outside of the grid or the matrix. But also islands can only be connected horizontally or vertically. So if we look at example 2, here we have an island right here, conformed of 4 pieces of land. But right here, this diagonal one won't be counted as a connection to this one. Same with this island conformed by 2 pieces of land or by 2 ones. Doesn't count as a connection to this. Therefore, we have a total of 3 islands. So what we're going to do is we're going to be using both BFS and DFS because for this particular problem we can actually use both, and it's not always the case, but just given the nature of this problem we can actually use both. There are some trade-offs. In my opinion, DFS is easier to code and visualize, but the memory complexity is not as efficient compared to BFS. So I'm going to show you both. I'm going to show you guys how to do both. And I actually think this is a good opportunity for you guys to practice both algorithms with this problem. So let's go ahead and show how can we work to solve this problem on the iPad. All right, so before we move on to actually solving the problem, I actually want to show you guys the difference between DFS and BFS and how does each algorithm traverses through the graph, because it's very different. And hopefully this will be a very visual example on how both algorithms behave differently. So just to remind you guys about the differences between one and the other is that BFS uses queues. Both of them actually use something to mark coordinates or nodes or whatever as visited. So we need something. We could create a data structure, or in our case for this algorithm, for this problem, we can actually use the graph and change the particular row and column that we're at from 1 to 0. So we don't really need to create a visited, but we could if needed for other problems. Also, DFS is always recursive. And DFS in particular uses stacks. You can use the stack of recursions themselves and not actually create a stack data structure, or you could create an additional stack data structure. Where in BFS, just remember that we have queues. All right, so let's start with DFS because you'll see the difference right away. So what I'm going to do is arbitrarily, let's say that in my DFS, every time I encounter a 1, which in this case is in the whole graph, I'm going to fire a recursion in the downwards direction. I'm going to fire another recursion to the right, fire a recursion upwards, and then I'm going to fire a recursion lastly towards the left. And again, this really arbitrary. It doesn't really matter which direction you set your recursions up. It really doesn't matter. It's just that in this case it just happened to be like so it would be easy to see. So what I would do is I'm gonna start here and I'm gonna say, okay, is this a 1? Yes. Change it to 0 and then go down. So then I go into the same function, right, because that's my recursion. Okay, I'm here. Is this a 1? Yes. Change it to 0, go down. So I would repeat the same until I hit a limit, right? Because I cannot keep on going down. So now what's my next direction? Okay, my next direction at the current recursion is go right. So then I would go right. Okay, I would try to go down again, right? Because in that new recursion, I would start from here. Okay, but I cannot go here, so now I try this one. So same thing. Okay, can I go down? No. Then go right. Go right again. Can I go down? Nope. Then I try right. Okay, right. I cannot go right either. So now I try to go up. So then I go up and I do the same. Can I go down? No. Can I go right? No. Go up. Can I go down? No. Can I go right? No. Go up. And then from here, I cannot go down, I cannot go right, and I cannot go up. So in this case, I go left. So then I try the same. Can I go down? Yes. Okay, can I go down? Yes. Can I go down? No. Right? No. Up? No. Then left. Then here, can I go down? No. Right? No. You know, we're following this right here, by the way. Can I go down? No. Can I go right? No. Can I go up? No. Can I go left? No. And by the way, if we're here, we cannot go down because it's already visited. We cannot go right because it's already visited. We can go up now in this case. So same thing. We cannot go down or right because it's visited, but we can go up. So in this particular case, the way I set this up, and again, this was arbitrary, but we went from here to here to here. In this case, the only place that we can go was here, then all the way down. Here there was nothing that we could do, so the only place that we could go was here and then here. Now notice how important it is that in order to get here, it was really fast. Well, quote unquote fast, but you know, we got there relatively fast, and then to get from here to here, it literally took us the whole graph. Why? Because that first search looks for depth. Now I'm going to repeat the same, but now with breadth first search. So essentially, and by the way, this is one of the cases where memory would, in this case, the memory that we used in the DFS was m times n. Now we're going to go with BFS, and I'm going to try to do this, hopefully in a very helpful and in visual way. So just to give you more or less the idea, because we're trying to travel through the nearest neighbors, right? So essentially we'll go like through this, then through here, then here, then here, then here. It's not exactly like that, but that's the idea. So we're covering the nearest neighbors. Hence why BFS is better for shorter path, and DFS is just better in general to see if anything is reachable or solvable. In this case, we would actually start, and I'm going to change the color again. We would start here, and if this is 1, I'll mark it as 0. And once, I'll add them to the stack, I'll pop them out. Obviously, after that is ran, I'll mark that row and column as 0, 2. From here, we will go here. And then once we go through this box, so to speak, because essentially, let's say that we're here, right? So I have this 2. So then this is the first one to pop. So then once we pop that, we also add this 2. Once that is popped, the next one that follows is this one. So obviously I would add this 2, which are the nearest neighbors. And once that I'm done with that, the next one that follows is this one. So I pop it from the queue, but I add this 2. Then the next one that follows is this one. I add this one, which is already added, and I add this one. And then I pop, I'm gonna start adding X's to signify that they're popped from the queue. So then I pop this one, and then I add the nearest neighbor. Then the next one that follows in the queue, obviously, would be this one right here. So I pop it, add the nearest neighbors, which are this 2. Then go to the next one, pop. The 2 nearest neighbors are actually already added. Because this added this one already, and this one added this one already. So we actually don't end up doing anything there. So now we pop that one. So the only one that we actually add is this one. And lastly, we pop this one, which doesn't do anything. So then I go back into the queue, I pop this one. So now I can only add this one. I pop this one in the queue. I can only add the one to the right. I pop this one. So now I go to this one, I pop it, and I add that one. So those are that is the way that we have the algorithm working, right? Which is like, it's not really like that, but it's very similar, right? Because we're following a queue, right? So that's the visual way of solving of how the algorithms behave. So now what I'm going to do is actually simplify the problem. I'm going to change this to, something very simple, where the idea here essentially, so I'm gonna do that, like leave that like so. So we're gonna be 0, 0, 0, right? And what we're gonna do is the following. We're gonna create a double for loop in order to access the wrong column. So I'm gonna go here, and let's say with DFS, I'm gonna say, okay, is that a 1? Yes, that's a 1. Change it to 0. I'm gonna have a count here, where every time I fire my DFS, I'm gonna add 1. Well, not every time I fire my DFS, that's wrong actually. Every time I encounter a 1 within the double for loop portion, I'm gonna add a 1. So here I found it, so I'm gonna add a 1 here, and then I'll fire my DFS. So I'm gonna say, okay, is that way? Can I find a 1 that way? No. Here, no, because it's a limit. Here, no, it's a limit. Here, yes. Okay, so I changed this one too, and then follow with my for loop. So I go here, there's no 1, no, 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 no. I go here, okay, there is 1. So I go here, I add 1 more to the count, and then obviously I fire my DFS, which, again, here I cannot go, not here, not here, only here. So I change it to 0, and that's it. I exit the DFS. So that's it, and there's nowhere else to go. So I just return the count, which is just a total of 2. And then I can do exactly the same with a BFS. It's just like the way that it traverses the grid. And in this example, because obviously there's not that many islands, you actually don't appreciate to see the difference in traversal between DFS and BFS, which is why I took the time to show with the grid full of 1s. So what I'm going to do now is show you guys how to solve the coding portion of this problem. Alright, so first thing we're going to do is create our count variable and assign it as 0. Then we're going to create our double for loop. So I'm going to traverse as long as I is less than grid.length. Then in my nested for loop, j equals to 0. I want this to run as long as my grid of i.length j is less than that, And then the next thing that I'm going to do is check that if in the coordinate I and j, that specific value is equal to the string value 1, and then I'm going to fire my DFS. So first I'm going to do this with DFS, because in my personal opinion, it's the most intuitive. So I'm going to do grid, and this is of type string. Then I have my row of type number and column. And with that, then we can do the following. I'm going to check if my grid row column is equal to 0. Because if it is so, if so, then it means that we can exit that recursion. If not, it means that it's a 1. So we just reassign that to a 0. And then we can follow on to find the different DFS functions. If row is bigger than 0, then we can do DFS grid row -1, comma, column. So if row is less than grid dot length -1, we can fire the DFS. So I can do grid row +1, comma, column. Same thing for the columns. If column is bigger than 0, DFS grid, comma, row, comma, column -1. If the column is less than grid row dot length -1, right? Because this would be the last index. So now here in my DFS, I can pass the grid. I'll pass the column value. The row value and the column value. And then I just return my count. And perfect, it passed. Now let's change this to BFS, where BFS is going to be using the same parameters. So this is going to be of type string. So we're going to use a queue. So I'm going to say let queue is equal to an empty array. And also I'm going to create an array of directions, where my directions are going to be the following. So this one is going to be add 1, so that's going to be going down. That is going to be subtract 1, that's going to be going up. That is going to be going right, and that is going to be going left. So it's down, up, right, left. So those are the directions. And I'm going to be doing the following. The first thing that I'm going to do is push the value of row and column into the queue. And I'm going to be saying the following. So while my queue is not empty, so while the length is bigger than 0, right? We are going to run a for loop. So I'm going to say for so iterate through the queue values. So let I equal 0, as long as I is less than the queue dot length, I plus plus. Then I want to pop the value all the way in the first position of the queue. So let current equal queue dot shift, and then I want to iterate. I want to fire or update the wrong column values in all 4 directions. For let direction in off directions, and I'm gonna calculate my new row value, which is current, right? 0. So this would be my current, right? Because literally that's what I'm doing here. Plus the direction 0. Of column, same thing. So now I'm using this value, right? that the row is out of boundaries if it's less than 0, or if row is bigger or equal than grid.length, column is less than 0, or my column value is bigger than the last index, right? Or zero. So grade R column is equal to 0. So if I find that scenario, means that I'm out of boundaries, or the box or piece of land is already visited, or that part of the matrix. So I'm just going to say continue. Otherwise, if there's no, if it's still good to go, is reassign. So it as visited, and then push that new row and column value into the queue. And I believe that's it. I believe that should work. And this was also accepted, and there you go. There we have our BFS and DFS. So I hope that this video was enlightening and educational. If you guys like this video, please give it a like, subscribe, and I'll see you in the next one. Peace.